Hi there. Welcome to a presentation by Exact Education. The goal of this video is to explain the normal probability distribution and how it may relate to numerical integration. To facilitate this goal, we will use a question to analyze and compute z-score values and hence probability values, and then verify them using numerical calculus, numerical integration. Our normal probability function, what do we mean by that? A distribution is simply a collection of data on a variable. Density functions describe how the proportion of data changes over the range of the distribution. In our case, it's a probability density function, and it sometimes is called the Gaussian distribution. It is a focus in much of the field of statistics. In order to create this probability density function, we need to compute the mean. The mean, we add up all the data values and divide by the count number to get our mean. We then want to have an indication of how spread out our numbers are below and above the mean value. So in order to do that, we calculate a variance number for each of our data points. So what we do for each of our data points is we subtract that data point from the mean and we square that difference. Why do we square that difference? We square that difference so that we get rid of the negative values. We've only got positive values, which we can then sum up, divide by the count to get our standard deviation number. If we didn't square, the plus and minus differences would tend to cancel out, and we wouldn't be able to extract the information in terms of how spread out the data set is. So the standard deviation is a number that tells us to what extent a set of numbers lie apart. Our question here is food production, and we want to know what is the probability of a bar sampled at random from a production line has a lifetime between 900 and 850 days, with a mean of 700 days and a standard deviation of 100. So what we expect to plot out in a normal distribution, if we plot the probability against the number of days, we expect to see a U-shaped curve. The mean gives you the peak value on the curve, which will compute out to be 0.4 or 40% probability of picking out a mean value. And what we want to do is effectively find the area under this curve between 900 and 850 days. In reality, this area will tend to be more at the higher end of the curve if we're using this example of a mean of 700, standard deviation of 100. So what we are doing is we want to convert our number set into a z-score, which is based on standard deviations rather than the actual number set, so that we standardize it and we can then use the z-score tables. So a normal distribution, 68% of the values are within plus and minus 1 standard deviation of the mean, 95% of the data set is within 2 standard deviations, plus or minus 2 from the mean, 99.7 or plus and minus 3 standard deviations from the mean. In this particular example, we've got a mean of 50 in our data set, standard deviation of 10. So we can see there, if we go up to 60, and then between 40 days plus and minus 10 days, we have 68% of our data points within that range. There is a mathematical description of the bell curve or the normal distribution curve, which is quite complex, as you can see here. The sigma label here is the standard deviation, square root of 2 pi. We have Euler's number here, which is a constant, which relates growth and decay in natural systems. It is a constant number, 2.718. And we have an exponent here that's based on the variance from the mean. So x is our probability, that is our sample. this micro is the mean, and this sigma is the standard deviation. So what in effect this exponent is the related to the variance for each of our samples in the data set. This is a complicated formula. So what's been done is to simplify working out the probabilities using what we call z-score tables. So what we mean by z-score tables is we take whatever values we've got in our data set. In this case, this example here, we've got 1010 as the mean, and we want to standardize we want to standardize our normal curve into standard deviations, plus and minus from the mean. So no matter what numbers are in your data set, we then convert, we keep the same shape of the curve, but we convert it into standard deviations. Why do we want to do that? We want to do that so that we can work out z-scores, which is related to the difference from our sample point from the mean divided by the standard deviation. So we're standardizing our where our sample is from the mean into standard deviations, and then we can use the z tables to convert our z-score into probabilities. And this short circuits using z-score tables the avoidance of computing this complex function. So in our case, we have probability between 900 and 850 days. So what we want to do is convert that 900 and 850 into a standardized form based on standard deviation and give us a z-score. So 900 gives us a z-score of 2.0, 850 gives us a z-score of 1.5. If you use the z-score tables to convert your z-score into probability numbers to avoid having to work out this function here, we then end up with these two probability values. So we have two probability values because we want to know the probability of picking out a bar which has got a lifetime between two bands of 900 and 850 days. So what we are going to do then to get our final probability is subtract these two probabilities from each other. And if we do that, it computes out to a probability of 4.4%, picking out a bar at random off our production line that will have a lifetime between 900 and 850 days. How do we verify if this is correct or not? Well, one way to do it would be to do integral calculus, get an area under a curve using this equation between two limits. It's a complex integral. There's a simpler way to verify it using numerical integration. So we can use Excel to do that. So what we have here is left-hand column, we've got the number of days, and we're going from 0 days, 50, 100. So we've got a resolution or a step change of 50 days. For each value of days, we're computing the probability based on our mean and standard deviation using this equation as a built-in function in Excel called normDist. We do that for each of the number of days, and lo and behold, what we plot out is our normal bell curve U-shape, where we look at the mean of 700. We can pick out this value here. We can see there is a probability of 0.4 or 40% of picking out a value of 700 days. There's a 40% probability of doing that at random. We are up between 850 and 900 days, so we're up around this region around here. If we wanted to have a more smooth plot out here, what we can then do is we can just change our resolution here and recompute it, which is the beauty of Excel. And in this case, we'll have to drag the values down so that we get a wide enough spread to actually show the full bell curve. So what we need to do in this case is we'll just delete this and we will reselect all those numbers all the way down to there and do insert recommended charts. Lo and behold, we pick out our probability density function and we'll enlarge that. And what we can see is, if we make that larger here, what we can see is 0.4 at our mean of 700, and we can see it tails off within 3 standard deviations either side. The probability effectively goes down to 0. So we didn't actually need all these numbers up here. So we can see our U shape here. So what we're doing is using the built-in norm disk function in Excel. So what we want to do now is we want to zoom in and do numerical integration from 850 down to 900 days. In this particular sheet with only a resolution of 25 days, then we've only got 3 values to work from here. We could use these 3 values to work out rectangular slices, area under a curve, and what we would do is we would take each of those values and multiply it. Well, in fact, we probably only would take those 2 values. We multiply the height times width of the rectangular slice. In this case, the width is 25, and we've got the probability values. In order to get a more accurate figure, what we've done on this slide is we've got a width of rectangular slice of 1. So we've calculated the height of our rectangular slice. It's got a width of 1. Height times width, it's got a width of 1. So all we need to do to work out our cumulative probability between 850 and 900 is to add up all the probability values for each day between those limits. And if you do the sum in Excel, which we've done here with this equation, we get a sum of 4.44%. So we've got a probability of picking out a bar at random off a production line. It's going to have a lifetime between 900 and 850 days is 4.44%. So what we've done is we've verified using numerical calculus our computational probability using the z-score tables. So what we've effectively done here is we've effectively zoomed in to our bell curve here. We've zoomed in down this area down here on this slide, and we want the area under the curve. So how do we get the area under the curve? We create 50 rectangular slices of width 1, and for each height of the slice, which is our probability number, so the probability number gives us the height, and we're adding 50 of those together. Area under a curve, we're adding 50 rectangular slices of width 1 day, and we get a value of 4.44 that verifies our z-score. So what we've tied together is a normal probability distribution function and how we can verify our computations using the z-score values using numerical integration. If we want exact values, then this is the formal equation, which is quite complex, so it's not normally done via this equation. It's normally done circumventing that complex equation using z-score tables that have been computed out for us. And if you want to verify it, we use numerical integration. If we want a more exact number, we could reduce the resolution down to half a day, for example, and we would get this figure more accurate. Thank you for watching, and I hope that has been beneficial to link together normal probability and numerical integration.